For our control project, we were given the task of designing a control system for a flour mill. Our problem statement reads, an environmentally conscious flour mill desires to install particulate control equipment to remove 90% of its emissions. The flour has a geometric mass mean diameter of 32 micrometers and a geometric standard deviation of 2.5, and its density is 1,400 kilograms per meter cubed. The volumetric flow rate through the existing exhaust stack is 500 meters cubed per minute, and the average flour concentration in the exhaust is 500 milligrams per meter cubed. Design a control system to achieve the desired removal. We're supposed to include a graph of the particle size resolved removal efficiency. So in this presentation, we will be going over the context for our air pollution issue, the discussion of the 3 potential control technologies, justification for the control technology that we chose, relevant theoretical and design equations, dimensions and operating conditions, calculated removal efficiencies, and then we will have our summary and our references. Here's what you need to know about flour. It is a complex dust consisting of wheat, rye, millet, barley, oats, or corn cereal, or a combination of these, which have been processed or ground by milling. The major components of wheat flour are protein, starch, and the minor components are polysaccharides and lipids. A large number of contaminants including silica, fungi, metabolites, bacterial endotoxins, insects, mites, mammalian debris, and various chemical additives such as pesticides and herbicides. You may be wondering why control technology is needed. There are health risks to industrial workers and their communities that will benefit from the removal of flour particulates in the workplace and the emissions to the community. Some health impacts include short-term respiratory, nasal, and eye symptoms due to the fact that it is a common irritant. Baker's asthma is something workers can develop from exposure to cereal flour and is also one of the most common types of occupational asthma. Some of the long-term illnesses can include febrile reactions, grain fever, lung fibrosis, allergic alveolitis, impairment of lung function, and chronic obstructive pulmonary disease. There are also some environmental impacts. Particles can be carried over long distances by wind and then settle onto ground or water. Depending on the chemical composition, the effects of this settling may include making lakes and streams more acidic, changing the nutrient balance in coastal waters and large river basins, depleting nutrients in soil, damaging sensitive forests and farm crops, affecting the diversity of the ecosystem, and contributing to acid rain effects. There are also multiple different stakeholders involved. This includes the flour mill workers. These people will be directly exposed to the particles and can develop some of those health impacts that we mentioned earlier. And the nearby residents who also may be exposed to the particles, but at a lesser degree. This still may affect their water quality of nearby lakes and streams.
The options we considered for the flour particulate removal were a cyclone dust separator, a baghouse filtration, and a wet scrubber. A cyclone dust separator uses vortex separation for particulate matter control without the need for filters. It uses gravity and a spinning motion to separate the particles from the air. The air is forced through a wider top in a helical motion and exits through a narrow bottom. The cyclone dust separator is highly efficient at removing small particles, but the efficiency falls as the particle size increases. The efficiency is greater than 98% for particles larger than 5 microns, but the efficiency falls to 90% for particles larger than 15 to 20 microns. The average diameter of flour is 32 microns, which means this may not have a high enough particle removal efficiency to meet the needs of the flour mill. The capital cost is $2.20 to $3.50 per standard cubic feet per minute, and 70 cents to $8.50 per standard cubic feet per minute for operations and management. The baghouse filtration method removes particulate matter through the use of a fabric filter. The air passes through a bag of fabric and the pollutants are trapped on the inside of the bag while the clean air passes through the fabric. Baghouse filtration is limited by high temperatures, corrosivity, and the stickiness of flour. The system has decreased removal efficiency above 275 degrees Fahrenheit. Since the bags are trapping the pollutants, the filters must be routinely cleaned to maintain the efficiency of the system. There are 3 types of cleaning methods: shake cleaning, reverse air cleaning, and pulse jet cleaning. Shaker cleaning is done when the system is shut down and the bags are shaken. This has a lower initial cost. Reverse air cleaning is when the system is shut down by air force. Pulse jet cleaning is when there are sudden bursts of air, which cleans the system. Overall, the baghouse filtration system costs between $3 to $5 per cubic feet per minute for installation, and for our flow of 17,600 cubic feet per minute, the total cost will be between $52,800 and $88,000. A wet scrubber removes particulate matter through the use of transferring the pollutant to liquid droplets and then removing the droplets. Wet scrubbers need a high moisture content to effectively work, and so misters are often added to increase the moisture content in the air. Flow rates needed for this system are 47 cubic meters per second or greater. Our flow rate is lower than this, and thus likely would not be effective at removing the particulate matter. The waste of the system is generated in the form of sludge. The cost of wet scrubbers is quite high. The capital cost for installing scrubbers on the top 50 sulfur dioxide emitting plants was $20 billion, which is significantly higher than any of our other options. The technology chosen was baghouse filtration, with a preference of the pulse jet cleaning system. Baghouse filtration was chosen because its efficiency was the best out of the three technologies, which was 99% for the size of the flour particles. It is the most cost-effective when properly designed and maintained. It also has convenient assembly with a modern design. The system can also remove other pollutants through fabric coating additions without the need for other technologies. Other flour mills wishing to control the flour pollution use the pulse jet baghouse filtration system, which shows that the system works well for flour removal. In the pulse jet, baghouse filtration systems are self-cleaning, which eliminates the need for routine cleaning and machine shutdowns. How does the baghouse filtration work? The baghouse filtration system removes particulate matter, specifically dust, through the use of a fabric filter. The dust is captured from the processing source through a duct system. The airstream is then passed through the fabric filters, also known as bags. The bags are cylinders wrapped in the chosen fiber material. The fiber material has small voids or holes that allow only clean air through, and the dust is captured inside the bag on the filter surface. The buildup of the dust on the filter is known as filter cake and will have to be cleaned. The cleaning method chosen was the pulse jet method. The pulse jet method contains a solid-state timer that self-starts the cleaning process. There are pulses of compressed air shot through the bags in the reverse direction of the airflow, and subsequently this dislodges the filter cake stuck in the filter media. The cake debris is then collected at the base of the filter in what is known as the hopper and discarded properly. Here you can see a simple drawing for a baghouse filtration system. The dirty air enters the system through the gas inlet, and then it is passed through the filter bags. The filter bags then remove the pollutants, and then once it has gone through this, the clean air exits the system.
There is a general procedure for designing a pulse jet filter that we followed to complete our control project. The first step is to specify the desired average tube sheet pressure drop. The second step is determine the operating characteristics of the baghouse. The third step is that the designer must obtain values for the variables in the field, pilot plant, or laboratory measurements. And the fourth step is finding the pressure drop using the face velocity. And this information is used to calculate the cycle average pressure drop. If the calculated pressure drop matches the specified pressure drop, the procedure is finished, and if not, the designer must adjust the face velocity and repeat the procedure. The air-to-cloth ratio, also known as the face velocity, was also an important relevant design equation. This is defined as the amount of air entering the baghouse divided by the total surface area of the filter fabric in the baghouse. This value determines the airflow capacity of the baghouse and must be optimized to balance the size of the baghouse, which is capital cost, with the pressure drop, which is the operating cost. The equation is displayed below. Pressure drop was another relevant design equation used in our control project. Pressure drop is a measure of the resistance to gas flow in the system. Baghouses with higher pressure drops require higher power fans to move air through the system, resulting in an increased energy cost. The total differential pressure is the sum of individual pressure drops due to the fabric, particulate layer, which also is known as the dust cake, and baghouse structure. An abnormally high pressure drop in a baghouse can be caused by a number of factors relating to poor design or setup. And again, below you can see the relevant equations that we used to solve for pressure drop. The dimensions needed to complete this project are area, industrial bag size, and the filter dimensions. For our area, we took the flow rate divided by volume and got an area of 99.61 meters squared. For the industrial bag size, the typical industrial bag size used is 1 foot in diameter and 30 feet long, and the system we use can fit 35 bags. The bags are cylinders with a volume of 23.55 feet cubed. For the filter dimensions, we took our flow rate and found that the dimensions are 19.5 in length, 8.25 feet in width, and 10.8 feet in height, and the filter thickness is 0.4 millimeters. Some important operating conditions for this project were the moisture/humidity, our maintenance requirements, and temperature. For moisture and humidity, it should be kept low to prevent condensation in the machine and keep the flour from solidifying, and therefore it needs to be dry compressed air. Some maintenance requirements are needed to be done on a daily, weekly, and monthly basis, and the filter must be replaced every 3 to 6 years. For temperature, it needs to be maintained between about 70 to 72 degrees Fahrenheit. The filter material chosen for our project was polyester fiber, which is a non-woven synthetic fiber that is made from a chemical reaction involving petroleum, air, and water. Some pros to this material are that it's of low cost and widely available, and it can handle and perform well under high heat, up to 275 degrees Fahrenheit, and it also resists abrasion. Some cons are it cannot perform well with moist heat, that is above 10% moisture, which is why in the previous slide we discussed that moisture and humidity needs to be kept low.
The pressure drop of our baghouse filtration system was calculated by the following equation. This equation is typically used for biofilter systems, but the previously mentioned pressure drop equation contained too many unknown variables to solve for this project. It was assumed that the voids or holes take up 40% of the polyester surface area. The unit airflow rate is the volumetric flow per unit of surface area and was found to be 16.47 feet per minute. By using these values and the equation for pressure drop, the pressure drop was determined to be 0.5184 inches of H2O per foot. This value is within the expected range of 0.5 to 1.5 inches for a new filter, so it can be concluded that our design will have an appropriate pressure drop. However, over time, the pressure drop will increase as the filter ages. Once the pressure drop is above 5 inches of H2O, it is considered too high and the filter will need to be replaced. The removal efficiency of a design is important to know to determine if enough contaminant will be removed. The overall removal efficiency of the baghouse filtration system is calculated by the following equation, where alpha is the solid volume fraction, Z is the filter thickness in millimeters, the Greek letter eta is the single fiber efficiency, and dF is the fiber diameter in micrometers. Single fiber efficiency is dependent on Brownian diffusion and interception. Brownian diffusion is the sporadic movement of the particle due to it being bombarded with other gas molecules in the air. Brownian diffusion is only relevant for particles less than 0.1 micrometers. Therefore, we will neglect diffusion in our calculation. Interception represents the directness or indirectness of a particle's path that will affect the removal. The path of the particle is impacted by the ratio of the particle radius to the fiber radius. In the equation, K is the hydrodynamic factor, alpha is the solid volume fraction, and R is the ratio of the particle radius to the fiber radius. While calculating the removal efficiency for our baghouse filtration system, many assumptions had to be made due to the lack of information. It was assumed that the solid volume fraction, alpha, was 0.77, the filter thickness, Z, was 0.4 millimeters, and the fiber diameter, DF, was 18 micrometers. The usual range for fiber diameter is 12 to 25 micrometers, so this is a valid assumption. Because removal efficiency of a filter is dependent on the particle diameter, a graph relating the two was able to be made. The geometric mean diameter of the flower particles is 32 microns. It was found that for this size of particles, the removal efficiency of the flower through the use of a baghouse filter is 99.9958%. In conclusion, the best choice of technology to remove more than 90% of flower particles with a geometric mean diameter of 32 microns is a baghouse filtration system with pulse jet cleaning. The filter material chosen was polyester due to its low cost and availability. The surface area of the filter bed was found to be 99.61 square meters, which is able to fit 35 cylindrical bags with volumes of 23.55 square feet. The polyester filter will have a thickness of 0.4 millimeters, and the bed will have a length of 19.5 feet, a width of 8.25 feet, and a height of 10.8 feet. The cost of installing this control technology will be between $52,800 and $88,000. The pressure drop of our design will be 0.52 inches of H2O per foot, which is within the acceptable range. The overall removal efficiency will be 99.9958%, which is well above the required 90%.